In this video, I'm going to go over the 12.3 notes with where we are going to talk about compound events. So our objectives today are to find the probability of mutually exclusive events and inclusive events. Some of our terminology are going to be simple event, compound event, mutually exclusive events, and inclusive events. So first of all, a simple event is an event that describes a single outcome. A compound event is an event that's made up of two or more simple events. We're going to talk about what that is as we go into the lesson a little bit more. Mutually exclusive events are events that cannot both occur in the same trial of an experiment. So obviously I can't roll a 1 and a 2 on the same roll of a number cube. Thus, those rolls are mutually exclusive. So when we talk about mutually exclusive events, it's the probability of two mutually exclusive events, A or B, occurring is the sum of their individual probabilities. So sum means addition. So for two mutually exclusive events, A and B, we're going to add together the probability of A plus the probability of B. So here again, if when a number cube is rolled that's less than 3, the numbers that are less than 3 are 1 or 2. So the probability of 1 plus the probability of 2, those numbers are 1/6 plus 1/6, and that would be 2/6, which reduces to be 1/3. So when we have that OR word, we're always going to add together. Now we're going to talk in a minute that sometimes we're going to subtract as well, but we're going to talk about when we're going to do that. So here, remember that the union symbol means OR, and the intersection symbol means AND. So I kind of call this one a smiley face and this one a frown. Whatever you need to do to remember them, sometimes you will see probabilities written like this, where the OR is a U and the AND is, we could call that an N, and the AND has an N in it. So that will work as a way to remember it. Just remember that the other one is the U. Here's our first example. Find the probability of the mutually exclusive events. A group of students is donating blood during a blood drive. A student has a 9/20th probability of having type O blood and a 2/5 probability of having type A blood. Explain why the events type O and type A are blood are mutually exclusive. Well, the key here is we know that a person can only have one blood type. They can't have more than one. So because of that, that's what makes this mutually exclusive. So then, because this statement is an OR statement, and it says what is the probability that a student has type O or type A blood, we're literally going to take this 9/20ths and add it to our 2/5. So when we do that, we get 9/20ths plus 2/5. To get this 2/5 to have a common denominator, we would multiply it by 4/4. Remember, 4/4 is 1, but when we multiply the 4 times the 5 down here, it gives us 20. So that's how we got 8/20ths over here. Add the 9 to the 8, that's 17, and remember we have a common denominator, so it stays common. So our probability of someone having a type O or a type A blood is 17/20. So check it out here. Go ahead and do this one and then come back to me. Each student cast 1 vote for senior class president. Of the students, 25% voted for Hunt, 20 for Klein, 55 for Vila. A student from the senior class is selected at random. Explain why the events voted for Hunt, voted for Klein, voted for Vila are mutually exclusive. The reason is that you only cast 1 vote. So each student only votes once, thus they are mutually exclusive. So if we then want to find what is the probability that a student voted for Klein or Vila. So that is adding together the Klein probability, which is 20%, and the Vila probability, which was 55%. 20 plus 55 is 75. That's our answer. Now let's talk about this terminology, inclusive events. These are events that have one or more outcomes in common. When you roll a number cube, the outcomes rolling an even number and rolling a prime number are not mutually exclusive. The number 2 is both prime and even, so the events are what we call inclusive. So I need you to notice here that when I talk about even numbers on a number cube, we got the 2, the 4, and the 6. And when we talk about prime numbers, we also have a 2, a 3, and a 5. Now over here, if we were to just look at this right here, we have 3/6 outcomes. And then if we were to also look at our prime numbers over here, we have 2, 3, and 5. So this is also 3/6. So what's happened here, because the 2 is in both groups, we've overrepresented that 2. So we're going to have to subtract 1/6. So we'll add the 3/6 to the 3/6, but then we'll subtract the 2, which is 1/6. So let's look at how this looks. There are 3 ways to roll an even number, 2, 4, 6. There are 3 ways to roll a prime number, 2, 3, 5. The 2 outcome is counted twice when outcomes are added, 3 plus 3. The actual number of ways to roll an even number or prime number is 3 plus 3 minus 1. And that minus 1 is, again, because we have the 2 up here represented in our first group and our second group, and we can't count it twice. We can only count it once. So the concept of subtracting the outcomes that are counted twice leads to the following probability formula. The probability of 2 inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. So for 2 inclusive events, A and B, this is probability of A or B. Probability of A plus the probability of B minus the probability of both A and B. So when you roll a number, an even number or a prime number, we had 3, 6 for our even numbers, we had 3, 6 for our primes, and then we had one number that was both even and prime, and we're going to subtract that one. So our total was 5/6. So recall that the intersection symbol means and. Okay, so find the probability of a number cube rolling a 4. So our probability of rolling a 4 is 1/6, because only one side has a 4 on it. And our even numbers would be 2, 4, and 6. So that's 3 numbers. And then a 4 is an even number, so we can't count it twice, so we have to subtract it. So if we add across the top, we've got 1 plus 3, that's 4, minus 1, that's 3. Remember, we got a common denominator, so we're good on the bottom. And then we know that 3, 6 is 1/2. So that's our answer. So again, what you need to remember is we always want to subtract the thing that is in both groups. Our next example says find the probability on a number cube, again, rolling an odd number. Again, we have 3 odd numbers, 1, 3, and 5, so we got 3/6. Or a number greater than 2. So our numbers greater than 2 are 3, 4, 5, and 6, so there's 4 of those. Now what we want to think about is what odd numbers are greater than 2? Well, when I think about it, it's 3 and 5. So that's 2 numbers. So we have to subtract those 2 numbers again because they are in both groups right now. So let's add the 3 to the 4. That's 7 minus 2. That's 5. So our probability of rolling an odd number or a number greater than 2 is 5/6. So go ahead and work this, check it out, and then come back to me. So this says a card is drawn from a deck of 52. Find the probability of each. So first it says drawing a king. Well, I know there's 4 of every card, so 4 kings out of 52 cards. And then there's 13 cards in every suit, so that means I have 13 hearts. Now we need to ask ourselves, how many of those hearts are kings? Only one of them. So we are going to have to subtract that because, again, it's in both groups. So we have 4 plus 13 minus 1. 4 plus 13 is 17. Minus 1 is 16. So this would be 16/52. And if I'm not mistaken, both of those are divisible by 4. So I think we end up with 4/13. Trying to find my answers here as our final result. Just trying to make sure. Yep, 4/13. That's our final answer. And again, remember, you can put this in your calculator, divide 16 by 52, push math in 1, and it'll give you the simplified fraction. So our next one says, what's the probability of drawing a red card or a face card? So again, our or was this symbol, face. So red or face. So how many red cards are there? Half the deck is red, so that's 26/52. Then we're going to add to it the face cards. Well, obviously we got a jack, king, or queen. Those are the face cards. We have 4 suits, so 3 times 4 is 12. And then we want to figure out how many of those face cards are red. Well, if half the face card or half the cards are red, then half the face cards are red. So we're going to subtract the 6 over 52. So here again, when we add the 26 to the 12 and we subtract the 6, we get 32 over 52. And again, that reduces to be 8 over 13. Sorry, I think that went off the screen. 8 over 13 is our answer. So on our next example, we're going to talk about how to draw a Venn diagram. So for this one, it says that we have 1,560 students surveyed, 840 were seniors, 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read the daily paper? So when we draw our Venn diagram here, we're going to use what it's asking us for in the end, the seniors and the paper readers. So I'm going to write paper over here as my categories. So first of all, it says that we have 840 that were seniors. So I'm going to put the 840 up here because that's our total seniors. And I'm going to put the 630 for the paper because those are our total paper readers. As I continue to read in this problem, it says the rest of the students were juniors. And it says only 215 of the paper readers were juniors. So I can tell that that 215 should go over here because these are the guys that were not seniors that were paper readers. Now what I need to do is find what goes in this area right here. So I need to figure out what goes in that area right there. So I see that I have the 630 up here. So I'm going to go 630 because that's how many paper readers I had. And then 215 of them were paper readers only. So when I do that, I can then find the number of, people that were both paper readers and seniors. So that's going to give me 415. So I'm going to put our 415 right here. Now, if I wanted to find out how many seniors didn't read the paper, then over here I could do my 840 minus my 415, and that's 425. Now, I want to tell you that the numbers that we're going to use are our big numbers. So we're going to use our 840 over 1560. We're going to use our 630 over our 1560. And then we're going to do our overlap. So we are going to do 840 over 1560. And then we're going to add to it our paper readers, which was 630 over 1560. But then we have to subtract our overlap. So we have to subtract this area right here because it's the overlap of the two. So we're going to subtract 415 over 1560. Because again, this is the number of people that were both. Okay, my pen is not working again as it likes to do. So, okay, so what we get when we do this is we get 1055 over 1560. Now I want you to go ahead and divide the 1055 by the 1560 and tell me what that percentage is. So when you did that, you should have got 0.676, which is 67.6%. So the 67.6% down here is the probability of a student that was a senior or read the daily paper. All right, so let's look at so this says of 160 beauty spa customers, 96 had a hairstyling, 61 had a manicure. There were 28 customers who had only a manicure. What is the probability that a customer had a hairstyling or a manicure? So again, we're going to use these two areas right here to draw our circles, okay? So got an oval here and an oval here, and I'm just going to call this hair and nails. Okay, so how many total did we have that got their hair styled? It says up here 96, so I'm going to put my 96 over here. And how many total got a manicure? It says 61 right there, so that 61 goes over there. Then it says there were 28 customers who had only a manicure. So that's the ones that are over here in this area, right here. So I'm going to put that 28 right here. Now, again, if I want to find the rest of this circle right here, this part right here, then what I need to do, this part, y'all see it, is subtract the 28 from the 61. And that's 33. So that's my number that goes here, my overlap. Those are the people that got their nails done and their hair done. Okay, now again, if I wanted to find out how many people just got their hair done, then I would subtract the 33 from the 96. And when I do that, I get 63. Now, this problem's asking us, what is the probability that someone had their hair styled or they got a manicure? So again, we got to take our big numbers. So we're going to take this number and put it over 160. So that's 96 over 160 plus our 61 over 160. And then we got to subtract our overlap. So we're going to subtract this right here. Those are the people that were in both groups. So we're going to subtract the 33 over the 160. When we do this problem, when we add together the 96 and the 61, and we subtract the 33 from it, we get 124 over 160. And then when we divide the 124 by the 160, we get 77.5%.